force exerted by a continuous charge distribution. So a continuous charge distribution looks something like this. So this is a charge distribution, and what we're going to do is we are going to surround this charge distribution so it appears to the outside as one complete charge. So what you're going to do in order to solve this is cut the source into small infinitesimal charges, dq. And each tiny charge will produce df equals 1 over 4 pi epsilon naught, which is k, q dq over r squared r. So first of all, you are going to see that each dq produces an effect on the point that we are looking at. And if each dq, let's suppose, is at a distance r from the source, then this force is going to produce a small df, as we talked about, at this point, which points away from it. Now our job is to find where the total force is. Now how do we do that? Well, in order to do that, we are going to follow these particular steps. First of all, you have to draw a coordinate system for anything that you are looking for. Then you have to choose an integration variable, for example, x, y, z, whatever, and then draw an infinitesimal small element dx. Write r and any variables in terms of the x, that one that you have chosen, and write dq in terms of dx, right? Your charge in terms of x. Put limits on integration and do the integration, or basically look it up in a table if you have them. So as an example, let's do example 1, which is uniformly charged thin rod. So in this case, we are going to consider a thin rod which has a length L, and we want to find where the force is. Now, this one is a one-dimensional case. This one's actually easier to do, but what I'm going to do is the one that's sort of two-dimensional in order for you to solve it. In this case, we will know that linear charge density lambda is equals to charge per unit length, and F will be integral over the rod df equals 1 over 4 pi epsilon naught q1 dq over r squared. So now let's look at a uniform line of charge. Okay? So if you have a uniform line of charge and you want to find, let's say, suppose that my charge is positive, right? And I want to find at point this, I put a test charge here. And I want to find the force that this exerts on this test charge when I place it here. Now how do I do this? Well, number one, we're going to follow the steps that we talked about. So we are going to divide the rod into small elements dz, right? Each small element has a length dz. So basically what we're doing is we are dividing this rod into small elements, each of length dz. Each of these dz carries a charge dq, right? So number two, this dz carries charge dq, right? And this dq is equals to lambda dz, where lambda is the linear charge density, right? And linear charge density, lambda, is given by Q over L. Step 3. Since dq is infinitely small, treat it as a point charge. Okay? dq is infinitely small. We are going to treat it as a point charge. So then this exerts a force dF on this test charge that is placed. So this will exert a force on my test charge, If my test charge is positive, my dF will be pointing away from it. And this dF mathematically is going to be equals to KE Q naught dQ over R squared, where KE, I always know, is 1 over 4 pi epsilon naught. Okay? So that's number one. So these are the 3 steps that we are going to take in order to solve this problem of a uniform charge density. Now, this is a 3-dimensional problem, right? So we are going to see if we can eliminate a few of these charges. So first of all, we are going to divide this into x, y, z. X, y, and z. And see if we can reduce this problem a little bit. So imagine this, I know I've drawn it this way, but this is actually coming out of the page, right? So this is going to be x, y, and z. So x comes out, y goes this way, and z goes up. So even though I should be drawing this as a dot here, it's coming out of the page, right? That's exactly how this should be drawn. The force along the x-axis, so the force along the x-axis is perpendicular to the paper, right? What does that mean? That means dFx is 0 in this case. It is coming out of the paper. Fz, now again, there is, since this is in the center, okay, now this is going to be the amount of force that this exerts downwards. It will have symmetrically another dq at the lower end that pushes it up, and these two forces will cancel each other. So plus z and minus z components will cancel, right? So dfz will also be equals to 0. Now what we're left with is dfy. What about the force in y? Yes, that will absolutely exist. Now what will it be? What it will be is dfy will be equals to df cosine theta. Now we have to find what this force will actually equal. Now we know that dq is equals to lambda dz from here, okay? By looking at this picture, this is going to be my y, this is going to be my z, and this is going to be my r, okay? This means 1 dq is this one, and if I look at this picture, what is this r squared? That r squared is given by Pythagorean theorem. Sorry, it shouldn't be not y. It should be y over z. I'm so used to just calling it x. But in this case, it'll be z squared plus y squared gives me r squared. Also, this angle is theta. So this implies cosine of theta will be equals to y over r. Now that I have all of these equations, I'm going to call this equation 3, this equation 2, this equation 1. I have all of these equations, and I'm going to call this one equation A. I can plug all of them into here, right? I can plug them all into here in order to calculate what I want, okay? So I'm going to change this, and I'm going to get dy will equal, what is df? Placing it from here. df will be keq naught dq over r squared. And cosine theta, I'm going to get from equation 3. I'm going to put it in here. That will be y over r. Okay? Now I have kq naught dqy over r cubed, right? So I will get, if I combine them together, ke q naught lambda dz, right? Lambda dz y divided by y squared plus z squared 3/2. Now how did I get that? Well, this is going to be, I combine these two, which is r squared times r will give me r cubed, right? And r squared is x squared plus z squared. So this means it's going to be y squared plus z squared, right? Plus square root of y squared plus z squared, right? This is 1 and this is 1/2. So I'm just going to add them together to give me 3/2. What's next? Well, now I can integrate. My integration now is over dz, as I see here. What will it be? Ke is a constant, comes out. Epsilon naught is a constant, comes out. Lambda is a constant, comes out. Y is a constant, comes out. And my integration is left over z over, oh, sorry, no z's, just 1. 1 over y squared plus z squared 3/2 dz. And what is my integration going to be over? It's going to be over L by 2 to minus L by 2. If this is the center, if I take this as a center, this is going to be integration over L by 2 to L by 2, minus L by 2. So I can place that into here. So it's going to be from minus L by 2 to L by 2. Okay? Now this integral is kind of complicated, but you can find the answer of this integral. It's in Appendix 1. I believe it's number 18. So the answer to this question is going to be equals to Ke Q naught lambda y over integration. It's going to give me z divided by y square root y squared plus z squared from L by 2 to minus L by 2. Sorry, this should be squared. Okay, and you can look up this integration. Once you have this, all you need to do now is plug these numbers into here and solve for it. Once you solve them and you know these answers, it is going to come up with Fy will equal 1 over 4 pi epsilon naught Q naught Q over y square root y squared plus L over 2 squared. That's what your Fy is going to come out. Oh, I forgot something here. So this should be dFy. When you take an integration here, you also have to integrate this side. So that will give you your total Fy. Sorry, I forgot to do that. Once you have this, you can simplify it when y goes to infinity, L goes to 0. That means you're just making this move further and further and further away, right? That means the effect of this becomes smaller and smaller until it almost becomes a point charge, at which point it is almost like an effect Q naught Q over y squared.